Yes, hello. Music's out. That means I'm starting. Hi, I'm Rafael. I'm a consultant from Oslo and an open source developer of a library called Byte Buddy, which brought me very close to JVM internals over the years. So I'm giving this talk here as an introduction to JVM performance because this is something a lot of us treat as a black box. We think of the JVM as this magical machine where we put in our code and it somehow makes the code faster, and we rely on that and we're happy about that. But today I'm trying to demystify a bit around how the JVM works internally. And I'm trying to avoid any complex concepts. I'm not showing you machine code. I'm not even showing you bytecode. I'm trying to build this on a level that is approachable to anybody, because as a matter of fact, it's not that difficult on this overview level. And I hope that this helps you in the future to better understand how your programs are actually run. But in order to give this talk, I have to have this disclaimer slide here. Because if you're watching this as a video now, for example, and it's far in the future, and this might not even be that far, let's say 2-3 years, whatever I say today can be very wrong, given to what the JVM implements. Because we're not talking about a specification today. The JVM doesn't say how it optimizes code. It's not written anywhere, and this might just change from one update release to another. And there's, of course, also different JVMs out there that do things differently. So one has to be very careful about saying what to do to write performant Java programs. And actually, this is a problem in practice. If you look things up on Stack Overflow, for example, and the answer to some problem or some general question is from 2007-8 or something, then these answers are often very much outdated. You find a lot about reflection, how it is slow, and about certain patterns that are very slow, like volatile reads or volatile writes. And a lot of has improved over the years. So always take these things with a grain of salt. And also, of course, I'm speaking about HotSpot today, the JVM that's included in the OpenJDK and in Oracle JDK. If you use another JVM, like J9 from IBM, things often work quite similarly, but there are, of course, differences between these slides. Before we dive into anything around JIT compilation or the compiler of the JVM, let's just review the model of how a Java program comes into existence. Because all of us, we write a program in Java or another language. We might use Kotlin, Scala. There's plenty languages out there that can be run on the JVM. And the reason for this is that all of these programs compile to Java bytecode, right? We take source code and use Java C or Scala C or the Kotlin compiler, any of these tools, to generate class files which contain bytecode. And bytecode doesn't really do anything in performance context. Java C is a very simple compiler to some extent. It's not simple as in simple, but it is not trying to optimize your code like a C compiler, for example. When you compile a C program, the binaries that you generate are already including all or most of the optimization work that is applicable to these programs. With Java, it's very different, and it's also a reason I think that a lot of developers don't know much about JVM performance. Because we can take this bytecode, and only at runtime, the JVM parses and processes bytecode and applies the optimizations there. And in this stage, it generates machine code that is then run on the processor. This will then be hardware dependent and will be operating system dependent. And this is also the reason that Java is only you only need to compile a Java program once, and you can then run it on any hardware that supports the Java virtual machine. Right. So, and today I'm trying to look into this last step where we get from basically a Java program to machine code and how the JVM looks into your code, how it learns about your code. Because that much I can say already. The JVM is an adaptive optimizer. It looks into your program at runtime. It profiles your program at runtime. And the same program can be run twice and result in very different states because the JVM translates things as they are run and how it observes your code being executed in practice. Right. So HotSpot has a system which is called tiered compilation. Any Java program starts out in an interpreted stage. And then based on this interpreted stage, programs can evolve to be compiled by two different compilers. In the past, in old JVMs, you could either choose to use the client compiler, which was basically the compiler used for desktop applications, where a short startup time was important, but then the efficiency of the program was not that much in focus. And for server applications where you would rather spend a bit of time starting your application, where things take longer to compile, but then you would yield a more efficient program. This would then be the server compiler, since server applications normally run for a long time compared to a desktop application, for example. Things have, however, changed a lot. It's not really working out that well anymore to say, okay, you have a client compiler and a server compiler. Applications are more polyglot. So today we have tiered compilation, where any program runs through a promotion stage, starting out with the least efficient way of running code, promoting things up to the most efficient way of running code. And this is done basically by the JVM by looking into your programs and finding so-called hotspots. And this is where the name comes from. This is why the Java virtual machine is called hotspot. It is because hotspots are basically programming parts of your application which are executed a lot. If you think of your average application, you use maybe something like Spring, and you have all these configuration classes. These are just executed a single time, and then your app is bootstrapped, right? These configuration classes wouldn't be hotspots. Well, if you have this REST API where you have this handler which is called 1,000,000 times a minute, then this obviously would be a hotspot. The JVM looks into your code and identifies where these hotspots are and compiles them accordingly. And this is what makes Java so much different to platforms like C, where this is not possible. A C compiler does not know what parts of your application are the most important parts, because it doesn't know how your application is used at runtime. That makes optimization work in C or C++ very tedious. You have to identify these parts manually, then you have to optimize your compiler setup manually, and compile accordingly. And if this use case changes, or if it might be changed even while the program is run, you don't have a chance to change this behavior without restarting. The JVM is very different, but we'll look into more detail there pretty soon. So these compilers are not normally referred to by the JVM itself. The JVM knows even a more fine-grained level. The interpreter is called level 0, and this is just machine code templating. So every instruction in the JVM, like adding to numbers or calling a method, has a template in the hardware's machine code. And every time you hit an instruction, you execute just this template with the values that you get. So you want to add 2 and 3, you will take this template to add the numbers 2 and 3 on your Intel processor if you run one, and then you execute that. And instruction by instruction, like it is in your Java program, your code will be run, right? After that, the JVM will at some point decide, okay, this is not very efficient. I cannot just run the program step by step. I have to look into the program itself, and I might find optimizations. Like, let's say this template adds the numbers 1 and 2. A compiler, even a very simple compiler, will be able to say, okay, the sum of 1 and 2 is always 3, so I don't need to do that anymore. And this is what a compiler does, or one of the things a compiler does. And the C1 compiler is of course applying these optimizations. There are, however, 3 levels on the C1 compiler, because as I said, the JVM looks into your program, it finds so-called hotspots or important parts in your program. And in order to do so, it needs to profile your application. It needs to collect data like how often is a method invoked, or how often is a field read, how often is an if statement true, or is it always true, all of these things. And based on this data, code can then evolve into level 4 compilation, which is then based on this profile that was collected in the C1 compiler, where these optimizations are applied. For example, a JVM might be able to prove by profiling that an if statement is always false, right? It might be just a constant value where it says if something, which is impossible to ever be true, and then the C2 compiler might take this information and say, okay, since this if statement is never true, I can just throw this code out. I don't even have to check the condition anymore. And basically, based on this profile, do something that you otherwise, without profiling, you couldn't do. And that's also a reason why Java sometimes, or actually many times, can be faster than a C program, because in the C program, at compile time and without having collected this runtime information, you cannot prove these things and then not apply these optimizations, right? And that's a big strength of Java and the JVM. That's why it's so popular as well for other languages, not only the Java language, because anybody can write a programming language, not care about performance much, give this program to the JVM, and then let the JVM do its magic, right? So the compilation unit of HotSpot is a Java method. So any method can be compiled in one of these stages. So you have a method like some business logic method. The JVM will start always in level 0 by walking it step by step through all instructions. And then the most typical pattern is to push this method right to level 3 after it is executed a certain amount of times. This is often 10,000 times. Once a method is executed 10,000 times, it gets compiled. For C1, it's often even lower. And then after having run this method sufficiently often, the JVM will at some point decide, okay, I know now how this method is used in the JVM or in the program I'm currently executing. Based on this information, I will now compile it in the server compiler in C2 at level 4. However, C2 compilation is rather expensive, and this is a trade-off you have to make, and this is something the JVM has to deal with. Compiling code takes resources, right? And these resources cannot be used to run your program. So the JVM internal runtime is competing with your business logic about processing resources and memory. And if a lot of methods are compiled, and this can be quite a heavy operation. So if your C2 compiler is very busy, because also profiling data, to collect all this profiling data, this has to be stored in your memory, right, in your RAM. And this RAM is then not available to your heap, for example. So if the code cache is already very, very full, then the JVM will put it into a simple profiling mode, where it collects very little data, but enough to at least decide if this method is worth bothering at all. And then once the C2 compiler gets available, it goes to level 3, and then probably to level 4. Another typical pattern is that something starts out in level 3, as we've seen before, but the method is trivial. And for trivial methods, like a getter or a setter, there's not really much to optimize, right? What can you do better in a getter? You can read a field and return it. There's not much a strong compiler even can do with that. So if the C1 compiler already realizes that this method is too trivial, it just puts it, basically it keeps it, but takes all the profiling logic out, because profiling is overhead, obviously, which you want to avoid in case that you don't need anything. And this is something that works very well on the JVMs, I can say that much, but it also makes the JVM very hard to observe. Because of course you might measure something, you might look into your application, you just started the server, and you think this is slow, what is taking so long? This is like an unacceptable margin. I promised my customer a latency of that and that many milliseconds. But in the beginning of a JVM, basically you have to reach the steady state. There's a lot of up and downs in performance. Using profiling, a program can actually be slower for a short while before it gets faster. And this is, of course, a problem, especially in finance. People try to find their ways around it. A typical way of doing that is, for example, you have a trading system, and you turn on the JVM with the program, and then you shoot fake data at the trading system, right? And once the JVM has basically is trained for this sort of usage pattern, only then the JVM is put online. And that way you can avoid these things, but in the average program, it is sometimes a problem, and especially when you try to observe things, it often is a problem, because you think you can already observe the JVM in its natural state, how your program will be executed at some point, but you are just experiencing these level shifts the compiler does for you. Right? Okay, so this is basically the general overview. How does the JVM or the compiler walk through your code? I'm today here to talk about what the C2 compiler does, because if you have a performance problem, typically the performance problem happens in code that is used a lot, right? And these hotspots, as the JVM name implies, are of course compiled by the C2 compiler eventually in the normal case. This is also an introduction. You can, of course, talk about the C1 compiler. You can also talk about the interpreter and their performance implications. And even though it's the last slot, I could just go on forever probably, but you guys want to go home at some point, so I'll focus on C2 and what it does. And the most important part to understand about a JVM and how it works and what assumption it makes is understanding call sides and the difference between monomorphism and megamorphism. And if this is all you take out of this talk, then I'm already very happy, because this is actually something that you can influence with your programming style. And I've seen this many times. I'm like, if you have a very data-intensive application that executes a lot of code, which is basically very bound to how strong its CPU is, then this matters. This is also something I should mention. It's great to know these things, but typically performance problems, of course, happen at the database level or some HTTP level, or you do microservices, so you have to marshal a lot of data and send it back and forth with HTTP. This typically consumes much more time and resources than the actual execution of your program. But this is something that is really worth knowing in my eyes. So what's a call side? A call side is basically when a method gets called. So where we have val bar, this is an execution of a method, right? And where this method is invoked, in particular, this is the call side we're mentioning here. So we're calling the method bar on the class foo, or an instance of the class foo. And foo obviously has a simple method implementation for bar. And in a trivial manner, you could just say, right, this is a simple method call. What do? I go to this method and I invoke it. But it's not that easy in Java. In Java, any method, unless it's declared final, is invoked virtually. So any method can be overridden. There might be a subclass of foo that overrides the implementation of bar, right? And you always have to check for that. And typically, especially in C++, this means that this dispatching of virtual method calls is much more expensive, because it doesn't sound like much, right? You only go to an instance, you check what the class is, and you check what the method is. This is like 3 things. But think about what your Java program practically is. It's a combination of a lot of invocations of different methods. So if you can just scrap off a bit of performance from a method call, this has a huge impact, right? And of course, the JVM's main goal, or one of the main goals of the C2 compiler, is to make these method invocations fast, because they are so common in a Java program. So typically, we have this indirection, and we have to find out what method to call actually. And the way this is done in many cases when a method is virtual is by doing a call on a virtual method table, or a vtable. So a virtual method table is basically a table, you can say that, where any method is listed by its signature, and it also contains like an address of the code that is representing this method's implementation. And this is, for example, the method table for the class foo, where the bar method at index 8, in this case, let's just assume it's index 8, points to system out println, hello, right? But as we mentioned, there might be a subclass of foo which overrides this method. And then this subclass sub has its own virtual method table where index 8 for method bar points at a different address, right? So any class in your JVM will get such a table where method signatures point to addresses. And there's a nice implication of single inheritance that Java has. The nice implication is that you know that any class can basically inherit its superclasses method table. So index 8 will always point to the same method. So the JVM, when meeting a call side where bar is invoked, already knows what index of the table it has to read. It just has to determine what table it needs to read. And this is basically the job that's left, right? So every time the JVM invokes a method that is dispatched virtually, it has to first check what type the class has, the instance has. Then it has to find the table of this type, the virtual method table, and then it has to go to the machine code address that is representing this method's implementation and execute it. And in practice, this means basically 3 macro operations, I can say, for any virtual method call. And this doesn't, again, it doesn't sound so bad. This is pretty straightforward. It doesn't take a few nanoseconds maybe. But in sum, since all of your Java programs are basically an assembly of many, many method calls, these 3 indirections are a lot and would matter a lot, because just being able to, let's just assume for the sake of the argument that any of these steps takes equally long time, then just reducing this 3-step approach by 1 step would mean a 33% performance increase for your application. And that is, of course, something that you will notice. So one way to do this, obviously, would be to implement a cache at the call side. So most programs don't have that much inheritance, as a matter of fact. Let's think of a getter method. Getters are rarely overridden in an actual program. So you might just remember, last time I encountered this bar call, it was on an instance of actually foo. And then I'll just remember the machine code address of the implementation of this bar method, right? So you do it once, and the next time you find it, you would have a cache. And other virtual machines, like Smalltalk, for example, which was a big influence to Java, they use these caches intensively. And basically, Smalltalk, performance debugging in Smalltalk often ended up by looking into where the caches would be too small to contain all dispatches, and then you would try to optimize it there. So now you would only check the class of the instance and then look up the address from the cache, which is much faster because it's local, and you would already improve the performance of your program. The Java virtual machine is not implying such caches. The Java virtual machine does something that is in practice much more performant, and it also leads to other performance optimizations being possible due to this optimization. And you might have heard this word, monomorphic. Sounds very academic, something that only people that are deep in the matter understand, but monomorphic basically just means a method only knows one implementation, or rather a class only, or a call side only ever meets a single class of an instance. So let's say foo doesn't even have a subclass, then it is trivial to assume that this dispatch will also always invoke the same method. Even though the method call by the conventions of the Java language is virtual, in practice it is not virtual because it's never overridden. So in the end, what JVM can do, it can put an assertion there to make sure that this really is an assumption that is true. And this sounds expensive, but these assertions are very cheap, and that is related to how hardware works. And then it can just go to the address that represents the implementation of foo, which is as simple as it can get, right? Yeah, and this is done for most call sites in your Java programs, as a matter of fact. So most methods are monomorphic. And other languages basically enforce this feature by not having virtual method calls by default. Like C#, for example, doesn't have virtual calls by default, which is sensible, because for the compiler, this matters a lot, for the JIT compiler. But this also enables a lot of things, like, for example, Mockito, which is the library I work on. What we do is we mock classes by overriding them dynamically, and this will only happen in your test classes. But if you run something in production, then these methods will not be virtual in practice. But for your mocks, we will override all methods because a mock isn't supposed to do anything, so we basically override all methods by an empty implementation. And this is how we can make this work without breaking performance in your production applications, right? Yes. So, as I mentioned before, the JVM starts with interpreting your code, then it profiles your code in a simple compiler, and then it pushes you over to a more performant compiler. And your call sides can basically be monomorphic and megamorphic at different times in your application. Let's say most call sides are monomorphic, about 90% on average, right? 90% of all your methods are never overridden. So these are just always inlined. JVM, or not inlined, linked. They are basically just replaced. All these method calls are basically just replaced by an invocation of the target address. Then there's also bimorphic method calls, and this is typically true for collections. You might have a call site that is calling list size or something, and you either use an array list, and you should never do that, or a linked list. So never use a linked list. It's also something you can take out of this talk. But then there's bimorphic because you have two implementations of this list size method, and then there's two call sites which is called bimorphic, and there the JVM does something similar to a direct link. It implements a conditional direct link. Everything above that is treated as megamorphic by the call side. So you have an actual heuristical cutoff value, which is that if you have three implementations of a class, or three instances of a class at a certain call site, then these method calls will be much more expensive than if you had two classes at a call site, right? There's a fallback for so-called dominant call sites. If a call site is megamorphic, so there's many classes seen, but one class in particular is met very, very often, right? you have an array list in 99% of all cases, but a linked list very, very seldomly, then this dominant target is still treated as if it was monomorphic, but all other types are treated megamorphic. And the JVM basically probably might start out with a virtual dispatch, and then after a while it sees, okay, this is actually always the same type. I now recompile this method in C2 to imply a direct link, and it optimizes it. And this might not even be true, because at some point you change your program, like let's say you have this trading app, and the behavior of this application is very dependent on what markets are open at that point, right? And then the Japanese market opens and your app changes its invocation pattern. So suddenly you meet other classes in your program, which might even be loaded dynamically at that point for the first time. So the JVM sees, okay, this is no longer an assumption I can prove to be true, so I have to de-optimize your program. I will probably fall back to megamorphic dispatch, right? And this is why also sometimes, and again in trading, this is common. Right? I mentioned this story where you would train an application with fake data before you put it actually online, just that the JIT compiler is ready. You might have applications that are trained ready for all sorts of markets. So you have an app that's ready for the Japanese market and an app that's ready for the European market. And once the Japanese market opens, you switch basically your load balancer over to this other fleet that you have trained for this other use pattern. This is something you can do, because every time this happens, this of course eats resources that otherwise would be available to execute your program, but since now the JIT compiler is using that, it's not available to you. And you have very little possibility to influence what C2 does, or C1 also, and this is for a good reason. You shouldn't configure too much, because it's very difficult and very easy to get wrong. There's of course flags for things, but generally, unless you really know what you're doing, and I include myself in the group of people who often doesn't know what I'm doing, in this context at least, so I wouldn't recommend it generally. Often the JVM is actually quite smart figuring out what's right? All right. Besides the reduced overhead of invoking a method, monomorphic callsides have a cascading effect by allowing so-called inlining. And inlining is basically the so-called Uber optimization in the JVM. Inlining means basically what it says. Inlining means that the JVM can take a method and it can basically copy-paste it to where the go-to statement was. Because if you just can go to some fixed address, you can just take the code at this address and copy it into the target space where the go-to statement would normally be. And this is something you wouldn't do as a developer, of course. You want to have your programs nicely normalized, where basically logic is only implemented once. That is the same logic, right? But for a JVM or a machine, it just reads instructions and it does what it says. If there's an indirection, that's an extra CPU cycle that is wasted on walking to some address. If this address is very remote to where you currently have loaded stuff into your processor, you probably have to read it from some cache or even the disk in the worst case, and this all takes time. So by inlining, basically we have now reduced this indirection to not be an indirection anymore. We now just have basically implemented what we would have implemented if this foobar method would be obsolete and just be called it as one place. And yeah, this is basically a big improvement, because it's called an Uber optimization, and it's quite intuitive if you think about it. The more code you have in a method, the better possibilities you will have to optimize this group of code, right? If you have 20 lines of code, then there's probably some redundancy that you can remove, something that you can reorder in order to get a positive effect. Well, if you only have a getter method, as I mentioned, there's not much you can do. A getter is just returning in a value. Well, if you have 100 lines of code, then there's probably something you can rearrange. And by inlining, of course, the mass of instructions that you can optimize upon grows and allows you to do things like removing stuff, right? And that saves you runtime again, because you do not waste cycles on these things. And I'll show you an example quite in a while, which is actually something that happens in practice, and you can look at it with a few tricks, right? Okay, so and this is something I can tell you by heart. This is something I've debugged actually in a production system, which behaved weirdly. As I said before, it's mostly applications that crunch a lot of data, that use a lot of CPU already, which will benefit of that. And this was a case like that. So you have maybe seen double-braced initialization, this thing, right? if you do that, this inner brace is a constructor, and by this constructor you can basically define code, and this looks more functional somewhat, because you can write the instructions that belong to the list initialization within these braces instead of having to define a variable and then you have to call variable add and blah, 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 right? The problem is that in this case, you are creating a subclass of ArrayList. And this subclass of ArrayList is its own type. And after what we have just learned about monomorphic and megamorphic call sites, if you have a lot of these, then any such double brace initialization class will be its own type. And suddenly, instead of having one type of ArrayList, which would yield a monomorphic call site, you might have 20 subclasses of ArrayList, which will yield a megamorphic call site. And if this is in a tight loop somewhere, this can have a severe effect on your runtime. In this particular case, we removed these double brace initialization array lists and gained about 90% performance, which surprises a lot of people. But it really basically hit something in the JVM's optimizer that destructed its inner workings. Because the JVM, the HotSpot compiler, what it does heuristics. There's no good reason to say 2 is the cutoff. We have bimorphic, but no other polymorphism, right? It just, the way the HotSpot compiler works is they look at a lot of Java programs. They think, how do most people implement something? And then based on these typical patterns, we will optimize the Java program. You have to make assumptions, otherwise you couldn't start anywhere, right? So this is why it is important to write sane and clean programs. And most of the time, it is enough to write basically a well-expressed Java application to hit all or most performance benefits of the JVM. And then there comes a cliff where you have to do very weird things in order to trick the JVM to do something else, where your code gets very ugly again if you just have to squeeze out the last nanoseconds of something, right? So besides that this is not a good style of doing things because your program also grows by adding classes, this is another reason why you should never use double brace initialization, even though unfortunately you still see it a lot, right? So how could we micro-optimize something like that? And this is something where what I mentioned, your code can get uglier by, if you want to do very specific performance optimization, sometimes your code needs to get uglier. So here we have an interface foo with 3 implementations. So this would be megamorphic, right? How can we force the JVM to have this dispatched monomorphic? Well, here's the trick. We implement a class foo instead of having the interface, and then we implement 3 static methods. And whenever we want to invoke the method, or one of the methods, we do this. We switch on the ID, and then we go through the cases, and then we invoke the sub-method that we actually want to invoke. This time, the JVM looks into your program and sees, okay, this is 3 method calls, they're all static. Static methods cannot be virtual, so they are monomorphic. I can inline things, and I can dispatch this non-virtually now. And these sort of tricks you sometimes see, especially if you click through frameworks that you use and they have some logic like this. Sometimes you actually see this pattern even. They do that to avoid a megamorphic call. And you should be very careful about when you use this pattern, but sometimes it can actually help you. But then you should profile things and look into things and be very sure that you're doing something that you want to do there, right? But this is something that is a possibility, and it's good to understand why people do that and then how this affects your program. It's nothing I recommend, though. So let's look at something that is a bit more real world. Let's say we have this log method, and this log method is static, and it takes a var arg of arguments. And then it prints all these arguments to the console. So we have a call side at system out println. The println call is a call side, but we also have arg2string. And arg2string you can think of in a typical Logger framework, you will get all kinds of instances, right, of all kinds of classes. This arg2string call, this call side, will very likely be megamorphic, right, because you will encounter all kinds of instances. So let's say we have this method where we log a string, an integer, and an object. Then we will have 3 types already. 3 types in HotSpot means megamorphism. This means that logging becomes very, very slow, and this is bad because logging is often sometimes we do a lot because we want to be able to debug and all these things, right? However, as I mentioned before, thanks to inlining, this monomorphic log call can be copied into the do something method. And this is something that HotSpot will probably do. It will copy the code out of log into your do something method. And now we have basically added more data to chew on, as I mentioned before. And thanks to this, we can, for example, see, okay, the array args always has 3 arguments. This is a fixed amount of arguments. So we can apply another optimization technique, which is called loop unrolling. So we just copy the loop body 3 times and put the arguments directly in there. And now we have replaced one loop with a single callside by 3 statements with a callside for each statement, meaning that this previously megamorphic callside for logging turned into a monomorphic callside. And this happens with logging frameworks a lot. Like simple logging for say, you hand out all these arguments, and if it's processed synchronously, then like print to the console, and then the JIT compiler will typically pick up the little code that is in this logging method and copy it in. And that's why if you have these very generic methods, like typically logging frameworks have, but also other frameworks, like think of Akka. Akka, the actors that take an object as a payload, right? This can be anything. And in these, if you write frameworks like that, and maybe some of you do, you have to be very careful about the inlineability of these dispatches. Because if the logging, if you had 100 implementations of the log method, which would be applied all around, then this initial inlining of the log method couldn't happen anymore, and then breaking all subsequent optimizations. And that sometimes you make a little change, which then prevents a whole waterfall of future optimizations, which then can have a big impact on your program. Yes. So this brings me to another thing. I'm a proponent of static typing. I like statically typed programs, but of course I'm a consultant. To some extent, I have to do where the money is, and that brings me sometimes to using JavaScript, unfortunately. And I'm not having problems with JavaScript in general, but there's interesting performance implications in JavaScript runtimes like V8 or also Nashorn. Because all the performance optimizations we looked into so far, they were based on types, right? So how does a compiler work on non-typed languages? Does it work very differently? And the answer is no. Inlining, monomorphism, megamorphism, all these concepts, that's nothing that's exclusive to the JVM. You find this in basically any virtual machine. And of course also in, for example, V8. So let's say we have a class, and this is JavaScript doesn't have class, but let's call it classes. An object rather than foo, which defines 2 properties. V8, in order to optimize this program, has a concept called hidden classes. So basically, when you define the foo object, the empty object, we define our first class, which we denote here by star, saying this doesn't have any members. And then we'll add x, so V8 will create a subclass for this instance. So we'll change the class dynamically, where we say x, which inherits from star. Then we define y, where x, y inherit from x, right? And now we define another object, but we change the order in which we define the fields, right? So now we define y first. So first we have the same class x, star, but now we get y and yx. So we have 2 different types. So JavaScript or V8 would have now failed to recognize the similarity of these types and might escalate the same thing on your JavaScript program by using a megamorphic dispatching method for something that otherwise would be monomorphic. That's why I think, because I'm doing a fair amount of performance-sensitive work, that's why I like static languages so much, is partly that. Compilers rely a lot on structure and on typing and in recognizing similarities. And by putting these similarities explicitly into your programs, you help the compiler to do a lot of optimizations. And this is generally the best performance advice you can give. Just write clearly structured programs, avoid too much virtualization unless you really have to put it in somewhere, and the compiler will be just fine. And this is, of course, true for dynamically typed programs as well. So in JavaScript, instead of having this random object definitions, rather have some factory or something. This will result in similar hidden types, and then you will get the performance gains out of that, right? So this is just a side note why types don't only matter for programming structure for you as a programmer, but also for JIT compilers and like all performance relevant tooling that can then take the structure you put explicitly into your application in order to find out how it can restructure your application to be more performant. Yes. Okay, so now we have gone through a general overview of how HotSpot or the JVM or most JVMs work with the tiered compilation. We have looked into Callsides and megamorphism, monomorphism. This is the second important concept I want to get across, and then basically all beyond that is bonus slides. I have 11 minutes left, but it's important to understand. Also it's basically to see why programs sometimes behave differently. So what we have here is a program where we create 20,000 random values, and then we will basically sum up these values 1,000 times, just to see, basically, this is of course not a useful program, but just to demonstrate something. And if the number is bigger than 50, we will add it, and if it is lower than 50, we will subtract it. This is important. So this here is a branch. Any if statement, any switch statement is a branch. And very similarly to monomorphism and megamorphism, it is of a big advantage if you know what you are going to do in the future, where a branch can be true or false. If you can predict if the branch will always be true, this is very similar to knowing that you will always dispatch a certain method of a type hierarchy, right? And ironically, there's a way to make this program much, much faster, because here we have random values. They might be, by a 50% chance, they might be bigger than 50 or lower than 50. So you don't have very good predictability here. In order to make it faster, you can add this sort method, and this program will basically become more performant. And why is that? Because you do something extra, right? You sort the array. But now by having sorted it, the JVM and also the processor, they can predict in the beginning that the branch will always be false. So they can optimize the program to basically prefer the second branch, the else route here, right? So for the first 500 values on average, 10,000 values on average, we will always hit false. And since we know that, and since we can now suddenly predict that, your program runs faster. And then for the last 10,000 elements, we will suddenly realize, okay, now we're always hitting the true branch, the if branch, I mean. And then we go there, right? So just as with megamorphism and callsides, it is always good if your program doesn't surprise you. And I mean, that makes sense, right? But in general, if you structure your programs in a way that allow prediction, both for the reader of your program, but also for the JIT compiler, this is always an advantage. So you cannot substitute virtual calls with branches because the same program applies. If you don't know where you'll end up, your JVM will have problems and your processor will have problems. All right. So I have 7.5 minutes left. Maybe one worthy mention is escape analysis. This is something a lot of people aren't aware of. And as you all know, allocating object costs time, and collecting garbage that these objects are in the end takes even more time. So what the JVM can do is when you allocate an object, and this is basically a list iteration, which is compiled down to this, you allocate an iterator here, and this iterator is invoked as long as it has new elements, and then the element is printed, right? This is an object allocation, and you would like to avoid that. So I've seen this, and I've argued with people about that, who don't like this syntax here, because it compiles down to that, and rather iterate over integers and dereference the indexes explicitly. This way, you save yourself from the allocation, right? However, the JVM is fortunately smart enough to realize that this allocation is very local, and it can then fully delete your allocation from your code and basically take it out for you. And it only can do this in very tiny scopes, so you shouldn't just assume that the JVM can find out that this object that you allocate somewhere is still in scope a few methods down the stream. The further you escalate the reachability of an object, the less likely it becomes that this allocation is deleted. But for very local allocations, it typically doesn't really matter. So keep your objects always in the smallest scope, and this way you increase chances a lot by allowing the JVM to delete this allocation altogether. And some people like to, for example, they have a long loop and then they allocate a lot of containers outside of the loop because they argue it will be much cheaper to reuse these objects throughout the entire loop. But the opposite is true, because if they are very deep down in the loop and just in a small segment of code, then the JVM might realize, aha, I can just allocate these values on the stack and I don't have to actually generate an object. Yes. Interesting in this context is also that code elimination, which is something many people get tricked by. what we do here is that we write a tiny benchmark where we want to calculate how much time it takes to sum up 20,000 random values, right? We generate an array with 20,000 values, then we take the time, then we iterate over all values and sum them up. And then we take the time again, and then we print out how long time this takes. The JVM will, however, look at this code and say, wait a minute, this segment here, this is not really necessary. So let me delete that. And this is the code you'll end up with, right? So this is a reason why benchmarking on a JVM is extremely tricky and done wrong a lot. And you find this in open source projects even. They praise themselves, look how little time this took. And then you look at the benchmark and you say, wait a minute, of course, this takes 0 milliseconds. It's not because your program is so good, it's just because it's not getting executed. So you have to be very careful here. As a matter of fact, system current time millis is a cached value in the JVM, and it is synchronized with the processor's clock every now and then. So if a synchronization happens between these two invocations, the time you get might even be negative, because the clock basically went too fast in the software and it's then resynced with the hardware. So it says then took -4 milliseconds, and of course that's not true. In order to do these things properly, you would have to be a bit more efficient about how you run your benchmark. And first of all, you have to, as we said before, train your JVM to run C2 compilation. And C2 compilation is only done after 10,000 runs on average. Also most of the times, actually. But there's rules sometimes that you cannot even rely on that number. So you have to at least 10,000 times run your benchmark before you can run your benchmark, because you want to run it while it is compiled, right? Then also we use nanotime, which doesn't suffer the problem that milliseconds time has. And then finally, we have to use the value somehow, and we have to use it in a manner that the JVM cannot prove us that we're not actually using it. So you cannot just store it somewhere and assume that that way it is basically safe to run the code. If we print it out to the console, the JVM cannot do an optimization where it says, you know what, I know you're not actually reading that, I'm not going to print this value, right? That's impossible, so we know for sure now that this is not happening. Of course, this makes it very verbose, and there are better techniques. Last thing I'm going to give you on the way is there's a great framework which is called JMH, which is bundled with the OpenJDK, and it is available for use, and there's a great tutorial around it, which allows you to make these tests much easier to implement, right? It is still easy to get right, but JMH takes care of a lot of things, like warming up your code. It does this properly, and it does it really in a way that you can be sure it's warmed up. It allows you to do this escaping of the result value very easily, such that code elimination doesn't happen. You just have to return the value from your benchmarking method, and then JMH will not print it to the console. It has a much more efficient way of doing that. Yeah, and that way you can spin up benchmarks quite easily, which can be dangerous if you do it wrong. But typically what you do is you write a benchmark, you post a benchmark somewhere if you want to prove a point, and then people will try to prove you wrong. And over time, you will get better at it and learn a lot about the JVM. So I learned a lot by benchmarking. And of course, if you have performance-sensitive code, it's very important to know what you're doing there. Right. So as I said, all of this is already bonus slides, and I always make too much slides. So let me just click through this. I have 30 minutes left, so I'll just end it here. Thank you so much. I'm Rafael. You can find me on Twitter. You can find my library Byte Buddy, which I appreciate if you check out on GitHub and on the internet, and also Documents for J is another open source project to run. If you have questions, I'm still here all day. Thank you so much for coming here, and enjoy the rest of your day.